Hi everybody, my name is Marcel van Loon, Technical Product Manager for Rambus's low footprint root of trust product line. Welcome and thanks for joining me. In today's presentation, I will try to shed some light on the topic of side channel attacks, what they are, why they are becoming more important, and how to protect your MCUs for them. Let's get started. So, what we're seeing in MCUs is that the original, let's say, microcontrollers were deployed in standalone devices. They were not connected to the internet, and the software they were running was limited, focusing just on the functionality of the device for which it was intended. Now, what we're seeing is that devices around us are getting smart, they are getting connected. That means that they have more functionality, more software running in them, they have internet connectivity. They will be reachable from a remotely located attacker. And there will be, let's say, information of interest or assets in those devices, in those MCUs that attackers might be interested in. So that means that the protection that these devices require needs to be improved. Where originally you had a microcontroller running a small OS, that OS was providing application separation, so that if a process crashed, not the whole device immediately went offline. That mechanism was used for a certain amount of time to also protect against more directed attacks towards the functionality of the device. That turned out to be insufficient over time, especially in the situation I was just mentioning, where you have the ability for attackers to actually remotely address attacks at a lot of devices at the same time. Meaning that we saw that a simple OS was just no longer sufficient to protect those devices. That gave rise to the proliferation of what we call trusted execution environments. Those provide an additional level of separation between the, let's call it, untrusted software, or at least the complex software component that is responsible for running the actual functionality, the features of the device, versus a trusted component that is responsible for the security of the device and maintaining the security of the device, even if that complex operating system, rich operating system environment was compromised in some way or form. Unfortunately, I think over time we've seen that trusted execution environments themselves are also fairly complex. They also get broken, and attacks get more sophisticated. So what we're seeing nowadays is that people are getting, let's say, there is more and more a drive towards getting yet another level of separation in an MCU, in a processor, where you have much more physical, hardware enforced security separation between what runs on in the main part of the device versus the security function. We refer to these little enclaves of security, roots of trust. These roots of trust are small, sometimes even processor-driven environments that run only security-related software, nothing else, and they have the task to protect the device operation, to make sure that you have a kernel that you can go to if the rest of the device is compromised, a kernel that you can query about the state of the device, that helps the device protect its own boot flow, firmware updates, and in that way also has the ability to protect any key material that is used while it is performing that security role. So key material, for instance, protecting the confidentiality of the software it runs, access keys towards cloud-based services, or maybe identity-based key material or identity key material for the user of the device. So these roots of trust are becoming more and more common, and it means that you have also a fine specified location, if you will, where key material tends to end up in a device. Once you do have keys in a device and there is interest in getting at them, there are many ways that an attacker can try to get can try to get access to the keys. The most common way and the easiest way, if you will, is at the top of this slide. Logical attacks, these are things that are attacking, essentially trying to exploit vulnerabilities in the software running on the device, or vulnerabilities in the security protocols that are running on the device. These attacks are relatively simple to mount. They don't tend to require direct physical attack, direct physical closeness to the device. As you go down this table here, the attacks become more complex, also more powerful, but they will require more knowledge from the attacker. Let's say more proximity to the device, the ability to measure more, or even to affect the device operation, all the way up to the point that where you see the invasive physical attacks, where you actually open up a device and try to probe it and try to get key material from there. For this presentation, we're focusing on the next level of attacks beyond the logical ones, side channel analysis, and I'll give you a very small intro, a 101 on what side channel attacks actually are. Essentially, when you are using key material to do cryptographic operations, right, people will try to find key material by looking at the algorithm itself. What side channel attack does is it tries to not look at the algorithm itself, but it will try to get information from, let's say, characteristics of the implementation of the algorithm. So you're not looking at the bits, but you are, for instance, looking at the power that is consumed while a certain operation is executed, or the electromagnetic radiation that it emanates. Or, as you can see here in the bottom left, right, there's a prime example of a very early side channel attack, where you have a safecracker looking at or listening to the clicking noises that the safe makes to try and get it open. So that's the type of thing that you can, let's say, consider side channel. You're just looking at how the thing is measuring at things it does, how it behaves, noises it makes, power it consumes as the algorithm executes. Now, why do we need this in the first place? As I mentioned earlier, devices are becoming of interest to attackers to get key material. Devices are also getting, let's say, more deployed in our environment. They have access to privacy sensitive information. They might control things that are dear to us. That means that the consumers of the devices, the users, might have concerns about it. But what, as a vendor, if your device gets hacked and becomes part of, let's say, maybe a denial of service or a ransomware attack, or privacy of your users gets attacked? So your reputation in that sense is now at stake. The device may be handling data that is valuable to you, movies or other data in the cloud that the device has keys for to access that. If those keys get leaked, somebody who didn't pay for the service or doesn't have a right to look at the information could try to attack a device and get access to your services in that way. These things have been recognized. So what we're also seeing in the market and in the field is that a lot of standardization is happening, where people say, okay, we need these devices protected. We're not gonna just trust the device vendors when they say, yeah, the device is safe and we did everything we could. We are actually going to put standardization and certification schemes in place to make sure that a third party has looked at the implementation and said, yeah, this looks good, this is safe, we've looked at all the angles, and this is good to go. What we're also seeing is that legislation is starting to ramp up to make sure that devices that are handling privacy sensitive data or that do represent access to sensitive areas in power grids or whatever, that the security of the devices is ensured, and the liability, if anything does go wrong, ends up at the device vendor. So for standardization, from a standardization perspective in particular, we see quite a number. I listed only 4 here, there are many more that are starting to look at what we call physical attacks towards devices. Most of those certification schemes have a standard, let's say a standard layout. They define different levels. And I have here an example for SCA, which is one of those levels that is gaining traction specifically in the IoT and MCU market. And the higher the level you're looking at, the more security requirements are, let's say, assured, are enforced onto the device. So for SCA is a methodology that is based on common criteria, which you may be familiar with from the smart card industry. What we're seeing here is that where you have SCA level 1, it's essentially a self-assessment. This is me saying that my device is fine. SCA level 2 is already a lab, an external lab, looking at, okay, what kind of things can I do to the device to try and break it? This is still black box. In other words, the certification lab doesn't really get insight on what's in the device, and they have a limited amount of time to attack it. But if you go from level 3 up, the demands become higher. So from SCA level 3, you start to see requirements on the physical security of the device. The lab will start to look at trying to attack it through side channel attack, as I was just saying, right? Looking at power traces, things like that. And this is common for most of the certification schemes that I listed and that we are seeing nowadays, is that there's a level at some point where that physical attack protection needs to be proven, if you will. Now, if we're talking about keys in a device, what things are typically of interest to an attacker? First and foremost, I would say the confidentiality keys, so the keys that protect your firmware, your software from being reverse engineered by an attacker. Because what you have to keep in mind is that the typical way an attacker goes about his setting up an attack, especially if he has a little bit of resources, he'll try to get hold of a device, he'll try to physically get the key material from that device, and then with that key material, try to he will look at the software that's running on the device, he will reverse engineer it, he will be hunting for vulnerabilities in that software, and then try to find an exploit on that software, that a vulnerability on that software that he can exploit remotely, so that he can scale the attack up and try to attack more than one device. That's quite an important set of keys to keep in mind that requires protection. Class keys are another class of keys, if you will, that are important. These are keys that are the same for all your devices. Attacker gets one key, he can get to all your devices. So these are things actually to avoid, but sometimes they are hard to avoid. Firmware upgrade or update schemes typically want to have the ability to send a single firmware image encrypted using a single key to all devices. That means there is going to be a class key in all devices to be able to decrypt that firmware. Other things are obviously of interest to protect to attackers nowadays are customer material. You want to make sure your device is protected against ransomware or identity theft attacks. Going back to my earlier statement about the reputation damage that means for your brand, but also obviously for the problems your customers will face if these things happen to their devices. But also not to forget, and I was again talking about the ability to scale the attack. If an attacker can find this vulnerability because he has been able to decrypt your firmware and he can take over control over many of your devices, then he's really after not so much the key material or identity information or anything like that. He is after the processor bandwidth and the network bandwidth that these devices represent. So he can use the devices that he might have hacked in that way, if you will, to mount denial of service attacks. Now, side channel attack is a fairly broad subject. So here is an attacker trying to get to a key that is in your root of trust sitting in your MCU. There are several levels of complexity that may exist in terms of how an attack is mounted. This slide gives an overview. I'll go into a little bit more detail further down the slides. The simplest one and the easiest to defend against is what we call the simple power analysis. This is an attacker looking at a single trace, and then with that, a single trace being a measurement on a device, be it power consumption or electromagnetic radiation or whatever the attacker has access to. And from that single trace already has the ability to determine what the bits of a key are that are being used. And I'll get to an example later. Differential power analysis or electromagnetic analysis is already a little bit more complex to mount. This is applicable for devices that have at least been protected against this simple power analysis scheme. Here, an attacker requires the collection of many traces of whatever he's measuring, typically power, and he'll do, let's say, a statistical attack, trying to find correlation between key guesses or between known data, if you will, and things that he actually sees the device execute. CPA is similar to DPA in the sense that it requires a correlation power attack, requires many traces. It's looking for a slightly different statistical approach, where for correlation, you're looking at correlation between your guess and the actual measurement. For differential, you're looking for the difference, whatever is difference between a known key and a whole bunch of random keys. These are, I would say, the most applicable attack and therefore also defense scenarios that we should be looking at. Template attacks are, I would say, a different class of attacks again. These are a type of attack where an attacker actually has a fairly large amount of control over a device, so much so that he can have a learning phase. He can actually run a whole lot of operations to the device with his own keys, with his own data, and then collect a database of traces. With that information, he is then going to run the operation that uses the secret key that he's after and see, can I match what I just measured with this particular operation to what I have in my database. These are, obviously require a greater amount of control over the device from the attacker. It requires this learning phase, it requires many more traces. These are also more difficult attacks to protect against because even the smallest amount of leakage will at some point show up there. Underneath all this is what we call test factor leakage assessment. Again, I will get into a little bit more detail there later. This is the mechanism that can be used to verify if a certain implementation shows leakage of information in the first place. So this helps you assess if specific countermeasures actually have the desired effect and effectiveness. A few examples. Simple power analysis. You just take the device you want to measure the power on, for instance. You put a small resistor in series with the power line. You just measure the voltage drop. That gives you a real-time assessment of what the current that a device is drawing, the power it is consuming. You can see it here. There's a single trace. In fact, here you're seeing an AES operation with, I believe, 10 rounds, where you see the same repeating pattern for every round of the AES operation. Next to measuring the power, you can also, as I mentioned before, right, measure electromagnetic radiation. That's one step more difficult for both the attacker as well as for the defender. For the attacker, because he needs to find now a good spot on the device where to measure. Right? This is not just a power line at the beginning that you can find, but you need to actually pinpoint your probe on the device to close to the logic that's actually doing the calculation. For the defender, this is difficult because you don't know upfront where the attacker will put the trace, and you don't even know typically where your protection logic ends up. Nonetheless, this defense against this is similar to what we saw just defense is similar for differential power analysis. It's just that you need to be more aware of the location of certain things. Right. So what would make a design, let's say, vulnerable to SPA, to simple power analysis? Here's an example of an RSA operation. This is a signature operation, typically sometimes used to sign for digital signatures, to sign certificates. And here in the middle of the code example, you see an operation that depends on a specific bit of the key being those D0 through N-1 bits. And in the middle, you see a multiplication operation that depends on whether a bit is 0 or not. On the power trace, that shows like this. When the multiplication is actually done, you see more power being drawn than when the multiplication is skipped. So here you can almost literally read the value of the key bits from the power trace. Clearly, this is something that you want to be avoiding. So making sure that you don't have any operations in your hardware that depend directly on key bits is, let's say, the first line of defense here. DPA, CPA is in that sense a little bit more complex. What does that look like? Here we have, for instance, a scenario where the hardware is already protected for SPA. So you're actually no longer able to recognize what goes on in terms of operations that depends on bits. So what is going on here is what the attacker needs to do is run a whole number, a lot of operations with different keys, different ciphertext, as an example, that gives different power traces. Then he'll let's say subtract those traces or correlate those traces. And try to find if there is a correlation, if there are peaks in there that might match common values in all those traces. That level of that kind of leakage will give a certain amount of insight in what's going on in the device and what values are being handled. You can collect as many samples as you have, as many traces as you have. Obviously, the more traces an attacker is able to collect, the more information he gets and the more sensitive his measurements become. So the better your defense, your protection mechanisms need to be. Then template attacks. I don't actually have an example to this, other than, as I mentioned earlier, the fact that if an attacker wants to mount a template attack, he does need to get access to a device. He does need to be able to put his own keys in, to put his own data in, build this library of traces in this training phase. The masking schemes and mechanisms I mentioned for SPA, for instance, they obviously help here as well. You can imagine that being able to build a database means that you have much more information on what's going on because you actually know what a specific operation and a specific data value results in terms of power trace. So the best defense against template attacks is actually to just limit what the attacker can do with the device. Limit key loading in the first place, so prevent him from being able to load his own key, make sure that any keys that are injected in the device and used by the device are themselves authenticated and protected. And you could, for instance, limit the number of operations that you allow to be done on a single key, which is generically a good countermeasure against attacks that require a lot of traces to be collected. It's a little bit summarized on this slide, where for the different SCA attacks, I think I mentioned most of them already. For simple power analysis, make sure that you don't have any key dependent timing. Something might take longer to do or shorter to do depending on the value of the keys. If you have certain operations that are sensible to this, for instance, if you're doing exponentiation and your exponent has a lot of zeros in it, and you have something similar to what we were showing just yet, where you have a no operation. If there's a 0 bit, then that shows up in the time taken to do a certain calculation. You want to avoid that. I mentioned masking. Masking is essentially a mechanism to make sure that you have, whenever you do need to work with keys directly, you put a random number, you XOR or you mask that random number, but that key data, sorry, with a random number, so that every time you do the operation, that data is different, and then you correct the operation for the random data that you use. That tends to hide, let's say, the correlation between traces with the same key. That doesn't work for all algorithms. So some algorithms require blinding or other forms of, let's say, hiding the key material. Blinding is, for instance, where you have operations where you are doing calculations not with the exact number of the key, but with a number plus some random offset, and then you will change that random offset on every calculation. And again, I mentioned it before, limit the number of users of a key to limit the amount of traces that an attacker can collect. Template attacks, I mentioned already before. I think we're clear on that. In general, any device that needs to protect itself against such an attack should avoid at all costs handling plain text key material inside directly, because anytime you move or do something with a plain text part of the key, that will show up in the traces, the power traces or EN. Now, you've done all this work, you've done all the masking and so on and so forth. Now, how are we going to make sure that that actually works in a real implementation? Because most countermeasures are applied at what we call RTL level, at a functional level in the design. In a device, in an actual physical device, you have gates and wires, you have delays, you have glitches. All those things can also lead to leakage, and if it leads to leakage, it might be giving information on key bits. So what do we do to get some assurance to that the countermeasures that we put into place are effective? For this, we have test vector leakage assessment. This is in some way or form doing a, let's say, a generic differential power analysis. You're taking your design, you put it in a physical implementation, such as an FPGA, or you can also even do it on a simulator, but that tends to be too time consuming. You run two sets of data through the device. You collect the traces in the same way that you do for a DPA attack. One set where you have a constant key and constant data that gives you a constant data set, if you will, with a constant set of traces, and one where you have varying key and data. And you compare those two, and if there are, let's say, peaks in that comparison over time, then those are points in the execution of the device where correlation is shown between the data you're handling and the power you're measuring. Does not necessarily need to be anything that is exploitable. It might not be correlation with actual key bits, but it does mean there is a point in the design that you should be inspecting, because there could potentially be leakage. So in other words, whenever Rambus, for instance, releases a DPA protected core, cryptographic algorithm core, we will have done this test vector leakage assessment to make sure that no peaks are found in this correlation. What we will be looking at are the types of figures that are here in the bottom right, where this shows the correlation between those traces, and the peaks should not come across the two bands or a certain bandwidth, if you will, to make sure that you have good leakage. And that gets you at least a level of assurance that you don't have any immediately visible leakage. Next to all the things I already mentioned before on power traces and sidechannel attacks, there are a couple of things that make the protection of MCUs against sidechannel attacks a little bit more challenging than for other devices. In particular, the fact that MCUs tend to be at least in a lot of cases, tend to be devices that are sold through uncontrolled distribution channels. So it should be, or it may be easy for an attacker to get his hands on a lot of those devices. If that's the case, it doesn't really cost much for him to, let's say, really go in and try to do measurements, even physical attacks, and break few, because they're not that expensive. If you're talking about a big processor in a PC or even in a data center, those things are harder to come by. They are much more expensive, much bigger also, which is the other thing, because MCUs tend to be fairly resource constrained. They have for themselves already a limited gate count. So there's less noise in the system from other operations going on, but there's also less room in terms of area and power to provide this protection. So that means that whenever you do have to protect your keys against these attacks, you want to make sure that you do that on as little logic or a little functionality in the device as you can. Oh, sorry, go back for a sec. The other thing that is something to keep in mind when designing protection for your MCUs is the fact that because they are so widespread, they are an interesting target for attackers. MCUs may be in devices, smart devices sitting in your home. You might get access to your own network in that through attacking that particular device. Or it might, like I said, it might control critical infrastructure. Or they're omnipresent, I would say, nowadays. So again, more and more reason for the attackers to focus on these devices. Again, I think I mentioned it a couple of times. The fact that you have the root of trust nowadays getting more and more traction in devices, I started the presentation with that, means that gives you an ideal location to also maintain the keys. If you keep the keys within that small secure enclave, the rest of the system does not need to worry about protecting key handling, wiping keys, masking. None of that needs to happen. Everything that has to do with the keys is done in that root of trust. So that makes it nicely controlled. It means the user of the main processor in that MCU doesn't need to be concerned with security, at least not security of the keys. So that's, I would say, a healthy and a very helpful step up towards getting the MCU side channel attack protected. Obviously, Rambus provides various roots of trust IPs that can be incorporated in MCUs, both for, let's say, small footprint, the RT260, as well as for the larger, more complex devices where customization of root of trust applications is required. And both of those IPs come with built-in side channel attack protection. Takeaways. I'm going to go over this very quickly. There are more and more of those MCUs around. They are more connected, so they are getting attacked more often. This is getting noticed by governments, legislation, certification, so there's more pressure to actually take responsibility for the protection. The SCA attacks themselves become more, let's say, more powerful, especially now that you have AI being used to, especially in the template attack area. And yeah, since it doesn't come for free, it's good to make sure that you have your keys, the use of your keys restricted. And yeah, last but not least, you should make sure that if you actually do have protection, that protection is indeed validated. And that was it for me. I thank you all for your time and your attention. And if you have further questions, then please feel free to visit rambus.com for further information. Thank you.